Welcome to the Preparing for the Oklahoma Science Test webinar. I'd love to introduce myself. My name is Brendan Finch. My pronouns are he, him. You can X at me or tweet at me or whatever at birdbrainfinch if that's something you do. I taught middle and high school science for 7 years in Los Angeles. I left the classroom to start rocketlit.com, which is our leveled science reading website. And in the last 5 years, we've been working on building Inner Orbit, which is focused on NGSS assessments and sense-making tasks. I wrote a lot of the assessments on the site initially. Most of those are gone because we have way better content on the site now. As we peel back the layers of the onion on these standards, we discover better ways that we can do things. And so we're always improving all of that. I spend a lot of my time right now talking to teachers and teacher leaders about ways to help with sense-making practice, so that if you are implementing three-dimensional standards and maybe you have a big assessment coming up, you can practice before the assessment and you have something to do after it. So we're building out some beta materials for that. If that's something you're interested in, you can always reach out to me or send an email after this webinar. But we'd love to support y'all with that. And so we have some new things coming out, which I'm very excited to share with folks when they're ready. They're not ready yet. We're still working on it. But to talk about the things that we're talking about today, let's dive into our webinar. So here we're talking about the OSTP science test. And our objective today is to analyze some released test items and to dive in some resources and strategies to build scaffolded practice for the science test and uncover actionable three-dimensional data. And that is the big idea. Our session length is going to be about 45 minutes long. We will dive into several things. So we're going to go into a middle school test item. Oklahoma's science test has y'all have a fantastic test. It's rigorous, it's beautiful. So we're going to look at one of the items, and we'll talk a little bit about three-dimensional standards, and then how maybe we can scaffold up to those standards. And within the lens of that, we'll dive back into a release test item, and we'll talk about some of Inner Orbit scaffolded items. So to give you sort of a frame for how to think about scaffolding sense making. That's the goal here. And then we'll also talk about using phenomena for test prep. So there is a frame that we hear people applying to things like standardized tests, which is that you prepare for it only during the time before the test. I think that's baloney. And so I want to provide you with some different resources and strategies to think about using phenomena throughout not just one unit, but throughout all of the units. In addition, think about daily do nows. So if you're not going to use phenomena throughout the unit, weave that into your lessons, maybe just go boop and kind of like boop a phenomena every day as a do now. And we also have these cool things called SCP practice problems, which I'll show you and walk you through. So if you're curious about any of this stuff, then we would love to show it to you. And if you have questions as we go through, please write your questions in the chat. By far, the most interesting pieces of these webinars are other people responding to things and not just me standing here talking, although I will talk all day long. So let's get started so that we can dive into the parts where y'all can share your ideas as well. Before we do that, I want to give you sort of a baseline for what we do and how we do it and what gives us some, inkling of how we can approach conversations like this. So what Inner Orbit is it's a very, very simple thing. So we do three big things. The first is we aggregate phenomena. If you don't know what phenomena are things that happen in the real world that can be explained with science knowledge. So we take things like research studies at the high school level and also sometimes the middle school level, or we package real world scenarios that are occurring at the elementary level, and we allow students opportunities to take what they're learning in class and apply it through the lens of something new. So what we do are all focused around assessment. So it's all practice and application. And so after students have gone through some instruction, or at the beginning of instruction, we find teachers using our phenomena or any phenomena and saying, I wonder why that's happening. Why is it that these turtles are, that there are different numbers of male and female turtles in these different areas where the temperature is different? That's weird. And then we'll give teachers and students different questions to pull from to sort of scaffold up to that sense making and give students the practice of application. So all of our questions are tied to very, very discrete parts of the standards, and teachers can pull from them or districts can pull from them. A lot of our districts will use us for common assessments, and a lot of teachers will use us for formative assessments or kind of like unit summative assessments or just little daily do nows and questions. And after those questions are answered, we drop all of our data into these really detailed reports. So we aren't built for anything but the three-dimensional standards. That's it. So when you look at something like an SCP, and here we're looking at the SCP of developing using models, what we're doing is we're breaking down elements from the grade level band of 3.5 and then the grade level band of 6.8. And within developing using models, there are several things. There are 6 different things that students should show and demonstrate and grow in proficiency on in 3.5. And then there's 7 things in 6.8. And so what we'll do is, because our questions are tied with really discrete parts of the standards, we'll say, all right, students did really well developing a model using an analogy, example, or abstract representation to describe a scientific principle or design solution. So maybe at the elementary level, they were really, really good with that. And at the middle school level, we noticed that students were struggling to develop a model to describe unobservable mechanisms. So that's probably a scale, proportion, quantity thing. We're looking at things that are too big or too small or too fast or too long for us to meaningfully observe, and maybe modeling of that is something that they really struggled with. So all we're looking to do is, when you sit down as a curriculum leader or a department chair or as a teacher, sit with your PLC, we want you to be able to look at data and say, it's this SCP, this cross-cutting concept, this DCI, and more specifically, it's this really discrete part. And then if you give more assessments after that, that you can say we moved the needle or we didn't move the needle with that and we got to try something new. So the goal is just giving you really, really clear data so that you can do better. And so if you want to try In Orbit Out, or if you want to meet with us to learn more about that, I'm going to drop a couple of links into the chat. If you want to schedule a meeting with us, then click on that Calendly link. If you want to just go explore the site on your own, like, I don't want to talk to that guy, he seems weird, then you can also click on that second link and you can just sign up for a pilot on your own and get started. But either way, we'd love to have you check out the site and see different ways that we can support you. All right, with that, let's dive into a test item example and analysis. So for this and for everything that we do, we're going to kind of really lean into the standards. Everything is going to be based around an actual standard. And so that's how we're going to frame everything that we do. And so the standard we're looking at today is MS ESS 1.3. And that performance expectation asks for students to analyze and interpret data to determine scale properties of objects in the solar system. And there are 3 dimensions to the standard. So this is science and engineering practice of analyzing and interpreting data. There's the DCI of ESS 1b, that's Earth in the solar system, just that there's a collection of things in the solar system and gravity holds them together. And then the cross-cutting concept is all about scale, proportion, and quantity. And the interesting thing about this standard is that students have to analyze and interpret data to determine scale properties of objects in the solar system. I think one of the most abstract things about the solar system and astronomy in general it is very hard to imagine how massive or how large different things are, because all we can see is just like a tiny, tiny, tiny thing. And so a lot of this standard is all focused around giving students lots of opportunities to engage in things that are massive scales, much beyond what they can observe, and providing the models usually or data to show those things. Okay, so we're going to dive into 2 different questions right now, and I want you to consider each of these questions. And so the first question is, Saturn, like other planets, remains in an orbit. What is responsible for planets being held in orbit? And the answer is that there is the sun's gravitational pull on them. I bolded the wrong element here, but the wrong answer here. But the answer is the sun's gravitational pull. And it's a simple question, simple multiple choice question. Second question that we're looking at is focused around, so this is from the OSTP science, where students are given this data set at the top, and then 2 different models of Titan, and a model of Titan and Saturn, and then a model of the sun and Saturn. And the prompt says, based on the orbital models and the table, complete the following comparisons. So students have to select the phrase that best completes each part of the sentence. The gravitational force between Titan and Saturn is blank. The gravitational force between Titan and the sun because of the blank of the interacting objects. And then, like it flips, the gravitational force between the sun and Saturn is blank. The gravitational force between the sun and Titan because of the blank of the interacting objects. So I want you to think on this a little bit, and I want you to consider these questions while you think on it. So these 2 questions are different. The first question, which is a multiple choice question, which again, I bolded the wrong answer. And then the second question, which it's still a multiple select answer question, but it is different than the first question. So what I'd like you to consider and then respond in the Zoom chat, which is, what is the difference between these 2 questions and why is that difference important? And I want you to think about what we as science educators are looking to do. So what is the difference between these two questions, and why is that difference important? That first question is where students are repeating a piece of knowledge they've more than likely discussed and seen before. So oftentimes we'll find questions like this where students are just representing what they know, but not applying their knowledge through a novel phenomenon or situation. Kind of the tricky part about questions like these is that oftentimes we'll find these questions with data sets and diagrams and models and maybe a whole bunch of text surrounding it. But the question itself is a simple memorization question. And so this question right here is it's something that just shows what students know. It doesn't show our ability to take that thing and apply it to something new. So the second question is different. So this involves a highly specific and probably a novel phenomena. This is a real thing that happens in the real world. We want students to take their understanding of scale properties and apply it to this very specific thing. Maybe students have studied Titan and Saturn, but most likely they have not. And so this provides a way for them to apply that understanding to this novel thing. And that understanding needs to be applied through the lens of analyzing data. So they need to look at data sets that they give them, the models. So that's visual data, and the actual, written data, the table of data. And they need to look at that they need to apply their understanding of scale properties through the lens of scale, proportion, and quantity, that cross-cutting concept. And so this type of question right here, these are what we call leveraging all three dimensions to grapple with a novel situation. And these are sense-making questions. And these are the types of phenomenal questions they want to build students up to. And so the question is, how do we get students to the point where they're successful on questions like this? So before we talk about that, I want to lay some groundwork and talk about 3D standards. If you're super familiar with 3D standards, wonderful. This will be review. You'll feel validation in your knowledge of these things. If you are not an expert on 3D standards, then it's one of these things that I think we just have to wash ourselves with over and over and over again before it really, really starts to sink in. At least that's how I felt myself. And maybe I'm more dense than most, but that's a scale, proportion, quantity type of question. So let's talk about what are three-dimensional standards to begin with. So this puppy right here is a three-dimensional standard. This is a performance expectation. And most specifically, the performance expectation part is at the top, where we expect this performance. Students analyze and interpret data to determine scale properties of objects in the solar system. And now within that three-dimensional standard, within that performance expectation, there are three things that are baked in. And so typically we see these referred to with the diagram that looks like this. So there's the DCI, that's what students know, that's the knowledge, it's stuff that we've been teaching for a long time. And when I was a student in classrooms, this was the only thing that we did. We just memorized and knew a bunch of things. But things have changed now. The world is different, and we no longer need to memorize a bunch of stuff because the sum total of human knowledge as it develops in real time is available. So you have it available to you right now, and you may be accessing other parts of it during this. And you also have it probably in your pocket, and so do all your students. And so frankly, just knowing things is not quite as important now. It's what you do with that. It's how you take that knowledge and you analyze the data. You look at similarities, you look at differences, you compare and contrast different data sets. And so that second thing is what students do. And these science engineering practices were pulled from research around what scientists are doing. How are they communicating? How are they taking in data? How are they analyzing that data? And those are the things that we want students to practice and learn how to do as well. And the cross-cutting concepts are, I think, the most interesting part of the standards as well, where students need to look at, okay, now can I take the performances that I have or any content whatsoever, and can I look at that through the lens of one of these specific things like scale, proportion, and quantity, or can I look at that through the lens of patterns? And so what patterns do I see here, or at what scale do I have to observe this system in order for it to make sense? And so those are a couple different ways that we take those standards and apply them to these things. And so all of those things are baked into those questions. So let's just go back to that question really quick and take a look at that. So this question asks students to understand scale, proportion, quantity. They need to understand scale systems of an object, and they need to analyze that data. All three of those dimensions are obviously present. And so if they understand that things that are more massive have a larger gravitational force, and that distance plays a significant role in how much gravitational force is being exerted, then they can answer any question around that by analyzing the data. That can be models, that can be data table sets, data sets in tables. And so those are a couple of different ways that we think about students scaffolding up or accessing a three-dimensional performance within this standard. Okay, great. So I guess the question is, so if we ask students questions about these three-dimensional standards and we want them to build up to these things, what are we asking them to do? And so what I want to think about really, really quick is two different things. And the questions that we asked and we just looked at right here are one way to think about these two different pieces of these two different performances that we're asking of students. So the first one was a representation question. And so this is a term that we saw Achieve using as we looked at their documentation. And so representation is one of those types of questions where students are communicating ideas they previously learned. So I used to do this in my classroom all the time, where I'd say, all right, so I'm going to talk about a topic in class, and then I'm going to give you an exit slip on that topic. And so you tell me what you learned in class today and regurgitate that at the end of the class. That's great if I'm trying to figure out on a diagnostic sense, like where students are at, if I'm formatively assessing them. So we're not even approaching a summative assessment yet. We're just kind of gathering a little bit of data on what did you learn today. That's great. And though it's good for learning development, is insufficient evidence of proficiency. So if we ask questions like that, we cannot make claimants. That we can't make claims or statements about student proficiency. All we're doing is we're measuring what they know, not how they can apply that knowledge. So sense making is the response to now what do we need students to do, because they can get all the knowledge they need on their phones or on a computer. So sense making is taking what to explain why or how of something new. And that's really all. There's a whole bunch to unpack there, but we need to explain why or how something's happening to make sense of something new. So students have seen something before, they are representing their knowledge. It could be a really rigorous representation of knowledge, like draw a quantitative model or write a CER statement or an essay to explain something. It could be a very rigorous performance, but it could just be a representation of their knowledge. And so what we want to think about are ways that students can make sense of something new, so to apply that. And these can be simple or complex, but they are summative assessments. And ideally, it's something where students are taking their learning and applying it to something novel after they have some initial understanding. So these performances, sense-making performances, are a demonstration of mastery of the standard. And it's the goal of the NGSS. And frankly, as professionals, y'all know that your ability to take knowledge, information, and skills from one thing and apply those things to another thing is highly indicative of your ability to be successful in new situations. And so training students and practicing with students, their ability to make sense of new things from, with the skills and the knowledge they had before, it's a life skill. And this is not just prepping for the science test or acing your science class. This is something that we all need to be better at. And so training and giving students practice and opportunities to make sense of novel phenomena and apply their learnings, their skills, the lenses, and the cross-cutting concepts is really, really important. So now that we've sort of laid the stage for this really big thing that we want students to do, how do we scaffold them up? How can we give them access to those rigorous performances through a series of small steps? And so to put a bow on that, final performance. So the end goal is sense making. And that's where, again, students use their knowledge through the lens of the cross-cutting concept and the SEP to explain why or how. But how do we get them up to this point? Well, what I would like to propose is that we should identify some invisible steps that we're asking students to take. And we think about this through the lens of dimensionality. So what dimensions, not what depth of knowledge necessarily, and what complexity of task are we asking them, but how much sense do they have to make of this phenomena and in order to answer these questions? And we also want to find ways that we can gather data on each step to best support those kiddos. And so what I want to walk you through right now is one of the ways that we can get students from the DCI understanding to a three-dimensional understanding. And again, the standard that we're looking at here is MS ESS 1.3, where students take that SEP, that DCI, and that cross-cutting concept and apply those things together. And I'm going to give you phenomena that we use on inner orbits. This is one of the phenomena we have for the standard. There are many others, which I will go in great detail walking you through. And this phenomena is, how would it feel to stand on Saturn? Probably not so good. But what we're doing here is we're giving students a lot of data sets and talking about planetary mass. We're talking about densities of common substances. And we're talking about this. There's a lot to unpack here, but we just want students to understand density and understand Saturn and understand this sort of scale model of all of these different planets in our solar system. And so all we have right here is just a solid setup of data for students to look at different densities and different attributes of these planets and what their composition is as well. And so with those characteristics, we're going to take that knowledge, that understanding, and we're going to ask them to answer rigorous questions. That first question, well, this is probably the last question they would ask them, but it's the first question we're going to go over. These are what we call sense-making questions. And so here's a free response question. This is one of the questions on inner orbit. And the goal here is to move students past what they need to do for the OSTP science test. And so to do that, we would ask them a question like, when looking up in the night sky, you're able to see other planets with telescopes or sometimes with your naked eye. That rhymes. From here, you cannot distinguish many differences. Use the data in Figure 1 and Table 1 to support the following claim. The planets can look very similar, but they have a lot of differences. So students need to apply their understanding of scale properties in the solar system through the lens of all of these data sets that we give them, and analyze that data to compare and contrast the differences between these planets. And so we gave them densities of different substances on Earth or common substances on Earth, and then also the densities of these different planets. So we just want students to compare and contrast using that data to generate a response to this. And so though this is a great question, it's a great place for us to aim for students getting up to. And if they're able to answer questions like this, they're going to have a much, much easier time with questions like that release test item. Now, given students will need to understand gravity to answer the release test item question, that's not a part of this, but this standard involves lots of different pieces of scale properties. So how do we get students up to this point where they can answer that question? So we'd like to propose that asking two-dimensional question is one of the ways to sort of like scaffold them up to that point. We could ask them questions about the DCI and the cross-cutting concept, or the DCI and the SEP. And in this way, we can sort of like bring them up to the point where they can answer those super rigorous questions that are free response, or those kind of like drop-down menu questions that we see on that OSTP science released item that we looked at. So the first type of question that we want to ask students, that we can ask students, are these DCI only questions. So can you answer questions about what? And if you can, it's great. Then we can move on to more rigorous questioning. So this first question says, Saturn, like the other planets, remains in an orbit. What is responsible for planets being held in orbit? This is really similar to the item that we looked at earlier. It's just the sun's gravitational pull on them. That's what's keeping everything in orbit. So their velocity and the sun's gravitational pull act in concert to help them just spin around. So this question is only asking about students' understanding of gravity and of the relationships between objects in the solar system. And it kind of hints at, you could say, scale properties because the sun is larger than these other planets. But honestly, this is just a DCI only question. Do students know what keeps planets in orbit? And it's just the gravity from the sun. That's the primary thing. Okay, so if we can get students to answer this question and we can gather data on just the DCI, maybe we can push a little bit further and ask more complex questions. So these questions can take the form of the DCI and SCP questions. So we can say, our friend Neil looks at the data in Figure 1 and Table 1 and says, the planets' masses must be related to their distance from the sun. Does the data provide evidence to support his claim? And students have to look at the data and look at the differences in what Neil thinks, what the data says, and answer this question. Is there a relationship between distance from the sun and mass? And initially, it may seem that that's true, but it doesn't hold up over time, over distance either. Anyways, this question is only getting at students' ability to look at the data that we give them and their understanding of scale properties of the solar system. And we're not really getting at the cross-cutting concept here. So that's not an explicit piece of this question. So instead, let's ask a question that does explicitly ask about that. So we have DCI only questions, DCI and SCP questions, or we can ask DCI and cross-cutting concepts questions. So this question says, based on the data in Table 1, which of these describes the scale of the model in Figure 1? And so we just want them to understand how this image that we give them shows the scale of this model. And this is a scale, portion, quantity question. They don't need to really analyze data here. They're just looking at scale, proportion, and quantity through the lens of this model that we gave them. Now, we're not asking about the SCP. We're just hitting the DCI and the cross-cutting concept. So asking questions like this can enable us to make claims. Now, maybe there are areas of the cross-cutting concept or of the SCP where students are struggling the most. Or we can ask them three-dimensional questions that we call sense-making questions and see, how they progress towards, the ultimate goal of this, which is answering really complex questions. So we say, when comparing planets made of rock or gas in tables 1 and 2. Which of these observations is an accurate representation of this data? So now we want to have students summarize the observations and all of the information in these questions and answer this question. And so this is actually, it's important because it's not just asking about the fact that there are larger versus smaller planets. It's not asking about density or mass. They have to compare the cooking oil and the planets, or the three different properties in a separate table to the planets. So this could be a memorization question, but the addition of an additional table and the comparison between those two tables is really what this question is getting at. So it looks like a knowledge only question, but students have to look at the phenomena, they have to read the tables in order to answer the question, which is the important piece of this standard and of this question. So in this way, we can ask questions at different degrees of sense making to scaffold up. So those first questions are core content questions, and they only ask about the DCI. So we're just asking about ESS 1B, do things. And then we can bump it up to a content and practices question or a content and concepts question. So say, now can you take that knowledge and can you weave in scale, proportion, quantity? Can you weave in analyzing, interpreting data? And if they can, or if there's a spot where they're struggling, we can also ask three-dimensional questions that get at that analyzing, interpreting data, the Earth and the solar system, and scale, proportion, quantity. And in that way, we can gather some interesting insights into where students are struggling or where they're succeeding. So I want to take you on a little field trip over into InOrbit's reports so you can see what those reports look like. So as students are answering questions on our reports, we can pull up different elements of the standards and see where students are struggling or being more successful. And so in this way, we can dive into something like LS1, and I'm going to click a button down here that says Show All Standards. This is our dimensions report, which looks at the different dimensions of the standards. And let's just say we ask some knowledge-only questions about structure and function. So we do have prior knowledge questions, and we have questions from grades 3 through 12. So if I was a middle school teacher and I asked prior knowledge questions from elementary school, I might find that students are struggling with the standard, which is that, or this element of this DCI, which is plants and animals have internal and external structures that serve various functions in growth, survival, behavior, and reproduction. At the middle school level, we asked questions about MS-LS11, LS12, and LS13. And what we're finding is that students understood cell theory pretty well. In middle school, it's a really light touch on cell theory, but they struggle with the idea that there are specialized structures within cells, kind of similar to what they struggle with at the 3-5 level, that have specialized functions. And they struggle with the idea that there are levels of organization within living systems, and those levels of organization all work together. And that's interesting because it's really similar to the thing they struggle with at the elementary level. So we might want to go back to elementary and talk about that there are structures that serve specific functions. And if that's the case, then we can move up to the middle school level and talk about how that comes to life in cells and in living systems, larger living systems like a whole organism or an organ system or an organ or tissues. And then we can also look at things like the SEPs, because each question is tied to not just a performance expectation, but a specific piece of an SEP. We can say, all right, so students struggle with planning and carrying investigations the most, or maybe they excelled with analyzing and interpreting data. We want to extend that, say, all right, let's generate some data and draw some causal or correlational relationships from that. But if we're looking to support students with something that they struggled with, let's dive into the 6-8 grade level band of planning and carrying out investigations and see actually where students need the most help. And well, where we've only collected data, the only places we've collected data is that they're struggling to collect data to serve as evidence, to answer scientific questions, or test design solutions under a range of conditions. That's probably most similar to a CER statement that sums up a lab or a set of data from an experiment. So you can probably imagine something on the OSTP science test where students are like so-and-so Marco goes through and does this experiment, and here's the data that they get. Write a CER statement to explain if their hypothesis is correct. So this is what this standard is getting at, and what we want to do is gather data on that to show that students are struggling with that or they're being more successful. And the same with the cross-cutting concepts. So I feel that they just don't get enough love, and I want to give them more love. And so if we're looking at something like energy and matter flows, and we identify that students are struggling with the idea that energy drives the cycling of matter within and between systems, then informally, anytime I want in class, I can say, whenever matter is doing something crazy, I'm like, hey, tell me how energy is impacting the system. Or if there's a change in energy, say, tell me what that's doing to the matter. Explain that through what's happening with the matter, how matter is cycling in this system. So in that way, you can take your understanding from the cross-cutting concepts or the data you're gathering from the cross-cutting concepts and ask students informal questions to sort of move them along the continuum of understanding those different things through the application of like earth science or life science or physical science. All right, great. So thank you for coming with me on that short little field trip to our reports. And let's dive into this is our last section. We got a little bit more to get through. We're not all the way through, but we're going to talk about using a phenomena for test prep. And we're going to still use this same standard. So I do not want to leave this because I think that diving really deeply into a single standard is going to allow you to appreciate how this could be applied through the lens of all different standards, whether you're an elementary, middle, or high school teacher. So again, we're looking at this three-dimensional standard, ESS 1.3, analyze and interpret data to determine scale properties of objects in the solar system. Students have to analyze and interpret data. They have to understand what the solar system contains, gravity, and all these scale properties of these things, and they have to look at it through scale, proportion, and quantity. So those are the three dimensions of the standard. So what I want to walk you through is how we could give students multiple different experiences throughout the course of a unit or a lesson sequence or a single lesson for a standard like this. And so I want to walk you through a little roadmap of what phenomena might look like through the course of this unit. And so let's just say we're starting out at the beginning of the unit and we want to ask students, why is Jupiter's storm so easy to spot from space? And this is going to be a whole class walkthrough and discussion. So I'm not going to ask any individual questions of students. I'm just going to give them this question, give them this GIF, and say, all right, so let's talk about what you notice and wonder about this giant red spot on this planet. And we can ask questions about the SCP, we can ask questions about the cross-cutting concept, and it doesn't have to be independent, it can be highly scaffolded, but we just want students to consider, and maybe as teachers or other students that do have this proficiency, we want to model the process of making sense of this phenomena. Let's say we've moved past this initial part of the unit and we want to get to the middle of the unit. So we want to ask questions about why aren't asteroids considered planets? And so in this way, we can have the class break up into groups and answer questions collaboratively around some printed and scaffolded phenomena exploration. So students can discuss the size of planets when compared with asteroids and how those things fall on very, very different scales. At this stage, we want students to be answering questions that target the DCIs, the cross-cutting concepts, and the SCPs, but the teacher can still add a lot of scaffolding. So they're not totally independently working, they're working in groups, and they're going to talk to each other about these things. So we can have some collaborative problem solving if we take one of our phenomena and assessment items and give that to a group of students to grapple with together. And then at the end of the unit, we want to consider an individual assessment, and we can look at what keeps the Trojans in their place. And so there are these groups of asteroids that are really just locked into place around the planet Jupiter, because Jupiter is pretty big and it impacts things around it in a very, very significant way. So in this final part of the unit, we really want students to engage in sense making independently. Teachers can still provide scaffolding, but removing those scaffolds at the end of a unit or a lesson sequence is very important because students will eventually have to do these things on their own at the end of the school year for the OSTP science. And so let's just say at the end of this unit, we've given lots of phenomena and we've looked at this Earth and space science standard through the lens of maybe 4 different phenomena. That's what we've looked at just from the InterOrbit website on this one standard. And we have lots of phenomena for each standard. But let's say we're worried that students aren't going to be able to grapple with these rigorous phenomena. And so I want to propose a different way that we can look at phenomena, and that is to go back to a prior knowledge standard. And so we're going to walk back from this middle school standard to a 5th grade standard that precedes it. So in this case, we're looking at 5 ESS 1.2, where students look at, representing data in graphical displays to reveal patterns of daily changes in length and direction of shadows day and night and the seasonal appearance of some stars in the night sky. So in this way, we can go back from that scale, proportion, quantity, and that analyze and interpret data to a different way where students are analyzing data, where they're looking at Earth and the solar system, but from an elementary level and patterns. And in this way, maybe we can ask some questions that are lower rigor than the questions that are at a very, very high level of rigor from what we were looking at before. And so we can walk back from maybe asking questions about why are some mornings darker than others? Or we can ask questions about how are constellations like calendars? Or we can ask questions about how can shadows help us tell time? And through all of these prior grade level band phenomena, we can give students and teachers opportunities to look at things that are novel and specific and to dive into the data sets that we give, but in a really low stakes way, where our students don't need to understand scale, proportion, in the scale quantities in the solar system, but they can use just these understandings from elementary school and look at these novel phenomena. And so teachers can also use these as opportunities to kind of model the process of analyzing data at a lower level of rigor so that students aren't so intimidated when they do see things that are at a higher level of rigor because they've seen lots of phenomena throughout this unit. So that's great. So just to review, some big ideas that we talked about is that practice makes perfect. We should use phenomena through every unit, not just during like test prep season, but constantly. And then using these different phenomena provides lots of opportunities for students to model and for teachers to model and practice transferring knowledge and making sense of something new. And then students are struggling with the on grade level content that lower the stakes. Give students something from a prior grade level band, and they can still have opportunities to engage in sense making, but we can also use those as ways to identify possible gaps or in knowledge or in skills. And if that's helpful, then I want to give you a couple of the structures to think about how to use phenomena throughout the course of a unit. And one of those is a daily do now. So this is a strategy we see teachers use where they do quick daily activities. So I used to call them do nows in my classroom. I know some teachers use warm-ups or bell ringers, whatever, that's what we're talking about. The thing you do at the very, very beginning of a unit or a lesson or of a class period. And so what this is, the intention of this structure is to build in rigor of questions from Monday to Friday. And so on Monday, what we can give is just a phenomena exploration, and observing a phenomenon, noticing things about that. Maybe as a teacher, I could project the phenomena up on the board. And we could say like, look at this data set here. What is the title of this data table? What do you think that means? What is the title of the phenomena? What do you think that means? Let's read a couple of these paragraphs. What do you think this is trying to say? What questions do you have? What things did you learn in reading about this thing? And then we can, on Tuesday, Wednesday, Thursday, and Friday, build up in the depth of sense making that we're asking of students. The first question can be, on Tuesday, it can just be a knowledge-only question. So tell me what about gravity or scale properties. On Wednesday, we can ask questions about the content and the cross-cutting concepts. On Thursday, we can ask questions about the content and the practices. And on Friday, we can have a doozy, rigorous sense-making question that students build up to. So if that's helpful as well, we have another structure that we learned from one of our partner districts in Maryland about phenomena transfer stations. And so what this looks like is you take all of the assessments on inner orbit for a standard, you print out 3 to 5 different phenomena with groups of questions for the same standard, and you set them at stations. And what's really cool about this is that in one class period, students might, in groups, move around from table to table and see 3, 4, or 5 different phenomena on a single standard during one class period, which is incredible. We want them to make deep connections with the content. We want to spark their curiosity, and we can ask scaffolded and up to rigorous questions because they're going to be applying their knowledge over and over and over. And as a teacher, you can walk around and you kind of facilitate the process, provide some scaffolding and some additional background knowledge or prompting to move things along. And some things to consider if this is a structure you're looking to use in your classroom is that students can support each other with pre-assigned roles. So you're the recorder, you're the fact checker, and you're the timekeeper. So each student sitting in a group is able to move things forward and knows what they need to do to be a productive part of the group. And those roles can obviously swap as we move from station to station. We recommend things like this are implemented towards the end of a unit. So after students have had some instruction, they understand some basic ideas, we can use this as a way for them to apply those ideas in a novel context over and over and over throughout the course of a unit. And probably have a whole class debrief afterwards. So before we say break, we'll come together and have a little conversation about what we saw in each of those things. And I think the noticings and wonderings and the connections that students are making and articulating verbally to each other is going to be a powerful part of this structure, because you're going to now look at, it's not scary to see new phenomena. If you get the basic idea, you can apply it over and over and over again to several different things. We also have these structures called SCP practice problems. And maybe you're like, okay, so I want a way for students to just practice. I don't necessarily want to put them in groups or do these do nows. So these are these content agnostic questions that we've written that are aligned to the K-12 progressions for SCP. So just the science and engineering practices. They're one-dimensional in that they are only aligned to an SCP and will use interesting and relevant phenomena that are not related to earth science, life science, or physical science. The goal of these is to just focus on SCPs only and build skill mastery and target specific growth. So some of our district partners will use these as diagnostics. They use them as cross grade level sort of common assessments where the 9th grade, the 10th grade, the 11th grade, and the 12th grade will all take the same assessment on analyzing turbine data or developing using models or constructing explanations and designing solutions. And in this way, we can look at data together in a content agnostic way and allow students to practice using these different skills without the burden of the content weighing them down, which in some cases that can provide some increased accessibility for kiddos. And a lot of the content in these is just like plain old fun. So we'll look at like mousetrap cars and silly little engineering challenges where students are applying their understanding of these different SEPs. From a purist perspective of the NGSS, content should always be woven into these. So this is why we call them practice problems. This is not a measure of mastery or proficiency. It's just a way to practice the SEPs in a low stakes context. That's it. That's it, y'all. Just like Russell here, I hope you get to enjoy some chocolate, and I am grateful that you spent this time with us. We analyzed some release test items. We dove into some resources and some strategies to build scaffolded practice. We looked through our inter-orbit scaffolded items. We talked about different ways, like using phenomena threaded unit, daily do nows, and SCP practice problems that we can support this process of growth towards making sense of novel phenomena and assessment. And I'm really grateful that y'all spent some time with me and are here to grow your practice. So in terms of next steps, if you'd like to find a time on our calendar to meet up with us, we would love to chat with you about InterOrbit and be more helpful. You can find a time on our calendar there if you'd like to pilot. You can also sign up for a trial account or a pilot on your own. If you're watching this as a recording, all of these links are going to be in the description of the video. And if you also are a social animal, you can follow us on social at InOrbit.edu or InOrbit NGSS. We post YouTube videos pretty frequently, so if you like YouTube and video content, then subscribe to our YouTube channel. And you can also email us if you're like, I don't want to do any of those things. I want to send you a digital text message. So you can email us at inquiries@interorbit.com, and we would love to answer any questions you have or be helpful. But that's it. Thank you all very much for being here, for growing your practice, for focusing, and for participating. I really, really appreciate it. If you have any questions, I'll hang out for a little bit, but I hope you have a beautiful rest of your day. Thanks, everyone.